So our last segment ended with some sample problems, and so I transposed the equation onto this paper. If this is endothermic, let's go ahead and answer this one before we begin. How could we produce more H2? Well, we could remove H2. That would drive it forward. We could remove F2. That would drive it forward. We could add heat to it. That would drive it forward. Or we could add HF, and that would drive it forward. Okay, acids and bases. Okay, so part of what you may or may not have done was that you were asked to use some, get some general definitions of acids and bases, and so I've recapped them here for you. Arrhenius acids are acids which, when dissociate in water, will increase molarity of H+. So an example is HCl. Because we start with 0 H pluses over here, we've got more H pluses over here, and therefore our molarity is increased. Monoprotic, diprotic, triprotic. Protic means H+. Okay, so monoprotic just means there's one H+, diprotic means there's two H+, triprotic means there are three. Arrhenius bases are those which will dissociate in water to increase OH- concentration. So there's no OHs over here, there's one OH over here, and therefore sodium hydroxide is an example of an Arrhenius base. Bronsted-Lowry acid is a proton donor. Bronsted-Lowry base is a proton acceptor. Okay, so what we want to realize is that there is something called a conjugate. Okay, and so the best way to show this is to just give you some examples. Okay, so if I have H2O plus NH3, my water is going to donate a proton to the ammonia, and it's going to form OH- and NH4+. So the water is the acid and the ammonia is the base. Okay? Now, you're also going to go backwards. So we have one proton here, two protons there. So this goes from 1 to 2, which means this is also a base. But because it's on the right-hand side, we're going to call it the conjugate base. And then going backwards, NH4 to NH3, we start with 4, we end with 3. That means it's giving a proton away, and that means that it is donating. So this is a conjugate acid. Okay? On the second one, the HCN is a stronger acid than water. So it will donate the proton to the water, and the water will be the proton acceptor. So in this instance, this is the acid, and this is the base, which means once this donates that proton, we get the cyanide, which means when we go backwards, cyanide has no protons, HCN has one proton, so this one is the base, but because it's on the right-hand side, we're going to call it the conjugate base. H3O plus, going backwards, becomes H2O. 3 protons here, 2 protons there, means that this goes from 3 to 2, and this is the acid. Since it's on the right-hand side of the equation, we're going to call it the conjugate acid. Okay? Now, the stronger the acid, the weaker the conjugate base. Or the weaker the acid, the stronger the conjugate base. Okay? So in this instance, this conjugate base is stronger than that base, which means the equilibrium will favor the left. In this instance, this acid is stronger than this acid, and therefore this one will go forward. Okay, we'll come back to this idea when we look at Kas. Now, what does it mean to be strong? A strong acid is one that is completely deprotonated. The protons come off, completely deprotonated. Okay? Which means, for example, when I have sulfuric acid, H2SO4, and it is strong, what that means is that that H2SO4 completely deprotonates. It is not reversible. It goes forward only. So if I have one sulfuric acid, I'm going to have 2 protons. Or if I have 100 sulfuric acids, I'm going to have 2 protons. If I have 1 zillion sulfuric acids, I'll have 2 zillion protons, and so forth. So sulfuric acid is strong and it's diprotic because there are 2 protons there. Nitric acid is HNO3 and it is also strong, which means when I put that in water, I'm going to have a single arrow only. And if I know how much HNO3 I start with, I know how much H plus I start with, just like I have up here. Except this one doesn't get multiplied by 2. And the reason that we care about how many protons there are is that that will help us figure out pH. Phosphoric acid is triprotic. There are 3 protons there, but it is weak. And what that means is that you have a double arrow, which means that each of these can be in equilibrium, and that each one of those will have a KEQ, which we're actually going to call a Ka. Nonetheless, when we pull 1 proton off, we have 2 protons left. When we have 2 protons, we pull 1 off, we have 1 left. We can take the one that's left, pull that one off, and get our phosphate. So we can pull the protons off one at a time, or we can simply say H3PO4, double arrow, pull the 3 protons off, and get phosphate. Okay? Usually and typically we'll want to take them off one at a time. Okay? Acetic acid is also weak, which means that when I pull the proton off, I do it with a double arrow, and then I have CH3, CO2 minus as the anion that's left. And one of the things that will help us moving forward is we see that when we pull a proton off, we get the conjugate base. When we pull a proton off, we get the conjugate base. And so what this tells us is, for example, is that H2PO4 minus is the conjugate base of H3PO4. Or nitrate is the conjugate base of nitric acid. Or acetate is the conjugate base of acetic acid. And that's important, keeping that in mind moving forward, because we need to recognize weak acids and their conjugate bases when we talk about buffers. Okay? Carbonic acid will be the last one in this segment, and it is also weak. And it is also diprotic, which means we can pull the protons off one at a time. So if I start with H2CO3, and I pull a proton off, what do I have left? Well, what I have left is bicarbonate. So bicarbonate is the conjugate base of carbonic acid. And then I have a second proton here, and I pull that proton off, and what do I have left? Well, what I have left is carbonate. Okay, so I have 2 protons that I can pull off. I can do it all at one time, just like I did up here, or more realistically, I pull them off one at a time. Double arrow means I'll have a Ka. double arrow means I'll have a Ka. And the value of that Ka will tell me the relative ease with which I can pull that proton off and whether the equilibrium will lie this way or whether it can lie that way. Okay? Now, one other thing before we end this segment is we see up here that water can act as an acid or a base. That's called amphoteric. It is amphoteric that it can do both. We see here that dihydrogen phosphate is the base or dihydrogen phosphate is the acid. Hydrogen phosphate is the base or hydrogen phosphate is the acid. Same thing down here. Bicarbonate or hydrogen carbonate can be the base or it can be the acid. It depends on what it's paired with and whether it's driven forward. The next segment will begin on how we relate this to pH.